Today I'm going to talk about the search for ultralight dark photon, and it is based on two papers that we recently published. Sorry, yeah, I should change this. It's this paper just published like a few days ago, so it's not work in progress anymore. But it's work in collaboration with a bunch of theorists in Stanford, and also some experimentalists from Stanford and SLAC. Okay, so here is the outline of the talk. First of all, I'm going to give you a very brief review about the ultralight dark photon, both from the theory side and the current experimental constraints. And the second part of the talk is the dominant part, and it's talking about the detection of the dark photon, and we are going to focus on this so-called light-through-wall experiment. And first of all, I'm going to give you a toy example where everything is simplified as a plane wave so that you can really get a kind of intuition on what's going on. And the key point for this dark photon detection is to realize that there are both transverse mode and longitudinal mode in the for the massive dark photon. And it turns out that for the light-to-wall experiment, the longitudinal mode of the dark photon is parametrically much better than the transverse mode. And actually, in the previous proposal about the light-to-wall experiment for the dark photon search, they totally missed the longitudinal mode. So if you can reinterpret everything you have for the search of the dark photon based on the transverse mode, you can probe a much larger regime in the parameter space. Okay, and then I'm going to get into the real setup of the experiment, this light-to-wall experiment. And I'm going to reinterpret everything we have for the current constraint. And also, I'm going to show you the future range estimation after you realize the importance of the longitudinal mode. And the third part of the talk will be very short. It's putting an additional assumption that in the second part, we only assume the existence of the dark photon in the model. The third part is putting an additional assumption that dark photon is actually the dominant part of the dark matter. Okay, and since you put in an additional assumption, the searching strategy will be modified accordingly. And we have this proposal, so-called this listening to the radio inside the Faraday cage. And also I'm going to show you the estimation of the future range. So both part of the talk, we are collaborating closely with the experimentalist in Stanford and SLAC. And hopefully we can get some money and carry out the experiment locally by our own. Okay, so first of all, a very brief introduction about the ultralight dark photon from theory side. So it's probably the most simple generalization to SEM model. So in SEM model, you got the 3-to-1 gauge symmetry group, and you simply generalize it by adding in additional U1 prime. And the gauge boson associated to the U1 prime is this gamma prime, so-called which is the dark photon, and that's the focus of today. And we assume that there is a mass term for the dark photon. This mass term can either be generated by the dark Higgs, or because this is a U1, or you can introduce a kind of a Stackelberg mass term for the U1 gauge boson. And there is a marginal operator that you can introduce in the theory, which is dimension 4, of course. And this epsilon is the prefactor, which is the kinematic mixing term, the kinematic mixing parameter. And I'm going to show you that the current experimental constraint for the epsilon is requiring epsilon to be very small when the dark photon is very light. So in this talk, I'm going to focus on the ultralight mass regime, which means the Compton wavelength of the dark photon is like 1 meter, or the mass of the dark matter is like 10⁻⁶ eV, so it's roughly like this size. Okay, so now we need to figure out what exactly this dark photon will do to our in reality. So one short sentence summary for that is it will mix with the SEM model photon, and it will modify the electromagnetic wave functions. So there are actually two different ways to look at the dark photon. Of course, they are just two different prospects. The physical observable shouldn't depend on which basis you are using, but it's kind of interesting to distinguish and important to distinguish those two bases. One is so-called the mass basis, which is you take the mass matrix of the photon and dark photon and you do the diagonalization respect to it. And in this basis, you get one eigenvalue, which is a vector, which is a massless photon, it coupled canonically to SEM model current. And the other is a massive eigenvector, And this is the massive hidden photon, and it will couple also kinetically to some model current, but with a suppression on the coupling constant with this epsilon. So when epsilon is very small, this coupling will be very small. And the other basis is so-called the interaction basis. This is doing the diagonalization in the interaction for the interaction terms. And one eigenvector is the interacting photon, just behaves normally, and the other is a non-interacting photon. So for this non-interacting photon, the only way that you can generate or have any kind of observable for this non-interacting photon is through the mixing term in the mass matrix. Okay, so both bases, they have their own good point and bad points. So you have to very carefully choose the basis that you work in, or else you will make some mistake, which is very subtle. And there are several important points for the dark photon. First of all, dark photon is totally decoupled with stem model sector if dark photon is massless. Okay, so this can be very clearly seen from the interaction basis, that you have the non-interacting photon, and if you also set the mass term of the dark photon equals to 0, then you won't have any mixing from the real photon to dark photon. This, in the interaction basis, the whole story is just like the neutrino. You oscillate one flavor neutrino to the other flavor of neutrino. However, if you shut off the mass mixing term, then you can only produce the stem model photon through stem model current, and the stem model photon will never mix to the dark photon, and you won't be able to see it at all. So that basically means all of the physical effect introduced by dark photon needs to decouple from the stem needs to be decoupled as some positive power of dark photon mass term. So it's either the prefactor must have a dark photon mass either square or to the fourth, and it's crucial to figure out which exactly is either 2 or 4 in this mass dependence. And also it's important to notice that for a massive photon, it has 2 transverse mode, which is just similar to the normal photon, and you have a longitudinal mode. Okay, and the key point of this talk is the importance of the longitudinal mode, which I'm going to tell you that in the light wall experiment, the longitudinal mode will decouple from the experimental the signal strength of the longitudinal mode will have the prefactor of m dark photon squared. Instead, if you just focus on the transverse mode of the dark photon, the signal strength will decouple as dark photon mass to the fourth. Of course, the dimension should be balanced by omega. Omega is the operation frequency of your experiment. For example, you can consider this dark photon cooling constraint coming from the sun, and the temperature in the core of the sun is like keV. So if you are talking about the very light dark photon mass, then the longitudinal mode is much more important than the transverse mode, because it doesn't have additional dark photon mass suppression. Okay, so here is the very quick review on the summary on the dark photon constraints. So you got this this chunk region is a so-called coulomb, which is doing the measurement to see whether there is any kind of a deviation from the Gauss law, whether the force goes like 1 over r squared. And if there is a mixing between dark photon and photon, then because dark photon is massive, then you will introduce some exponential decay behavior into the potential term, and you will see the deviation from the Gauss law. And here, the horizontal branch or the solar cooling, those are the constraints coming from the stellar cooling process. So imagine that you have the sun, and also you have the mixing between photon and dark photon. Then the sun will not only radiating photon, it also radiate the dark photon. If the dark photon is produced so efficiently, then it will change the evolution of the star, and that's the constraint coming from the stellar objects. And actually, very importantly, those constraints has already been calculated before for example for the solar cooling, but they also missed the original calculation missed the longitudinal part of the solar cooling, and it was pointed out by Maxim Postloff several months ago. That is the importance of the longitudinal mode, and that will totally correct the scaling behavior when you take the dark photon mass to be very small. Okay, so that's actually serving us as a kind of a motivation, because if people miss the longitudinal mode in their solar cooling calculation, then they may also miss something else in their other calculation. And it turns out that the same group made the proposal for the light to wall experiment, and they also missed the longitudinal mode, and that's why we start our calculation. And this weird shape constraint is coming from the SAMB, and the physics behind it is very interesting. So imagine that in the very early time of the universe, the temperature is very high, and then you will have a plasma of electron-positron, and the plasma electron-positron plasma will introduce the plasma mass to the real stem model photon. And when you're gradually cooling down the universe, the number density of the plasma is reducing, so the plasma mass is decreasing. So for example, if you have a dark photon like 10 to the minus 9 eV, there will be a stage where the plasma mass of real photon match precisely equals to the dark photon mass. And there will be some kind of a level crossing effect happening. So that will convert the SAMB photon to dark photon, and that will change the spectrum of the SAMB. And that's why you got the SAMB constraint. And those weird edges are coming from the different stage of the universe. For example, this edge is coming from the reionization, and this edge is coming from the recombination. Okay.
Why does it look so flat? I mean, as a function of the dark photon? What would you expect?
I don't remember the detailed reason. It's just the result coming from the calculation. It's kind of complicated, because you have to firstly calculate the transition rate and compare how this distortion of SAMB compared to the real observation of the SAMB. So you have to do the chi-square, and if you shift or distort your SAMB spectrum in different energy regime, that will also cause some difference. And I'm not quite sure why this is flat, so that's a good question. Okay, so that's everything about the dark photon, the current situation of dark photon. So any questions so far? Yes.
So you're saying the sunbound is wrong. So
the sunbound was wrong, but this is the correct one. Yeah. So previously it goes like this, which is much steeper than what the current correct bound on, because it's goes steeper because it has a higher power dependence on the dark photon mass, and that's why the slope goes like -4. And now, after you realize the importance of the longitudinal photon part of the photon, the constraint goes like -2 at the slope.
So up to what mass?
Yes, there will be tons of constraint over here, like GeV mass of dark photon, and the constraint for the sun stop at keV, which is the
so all the way to keV, we should still think the longitudinal mode is very important.
Yes, that's right. Okay. So once the typical frequency or the typical energy of the process is much larger compared to the dark photon mass, then the longitudinal mode will be more pronounced because of the Goldstone equivalent there. Yes.
How did you get the phase from the planets?
Yeah. So those are kind of some bizarre constraint that is still making the assumption that the dark photon is mixed to the photon, and that will introduce some kind of effective mass to the photon, and that will change the say you have the measurement of the magnetic field distribution on the Earth or the Jupiter, and if you have mixing, if you give a kind of a mass term to the photon, then that will make the distribution not purely dipole or quadrupole, and the deviation is actually can be calculated, and that's how you put in the constraint. Okay, so now let me tell you very briefly about the light wall experiment. So one sentence for that is just detecting the fields leak through the shield. Okay, so here is the cartoon picture for the whole setup. You have a shield, which is a perfect conductor, assuming it's grounded. And on the left-hand side of the wall, you put in the source of the field. And on the other side of the wall, you put in the field sensor. And the source of the field, of course, will produce the electric magnetic field, and it's totally blocked by the shield. So if you only have the stem model electric magnetic field, the field sensor will feel nothing. However, if you also assume the dark photon exists in the story, then the source of the field can also source the dark photon field. And the dark photon field, since it's so weakly coupled to thermal sector, so it will not be able to feel the existence of the wall, and then it will leak into the other side of the wall. And if the field sensor is sensitive enough, then it may be able to tell whether you have already put in a source or not on the other side of the wall. Okay, so now let's do a very quick estimation on the size of the signal. So first of all, let's assume that the source of the field will generate a field strength on the left-hand side of the wall as E or B. Okay, the source field is E and B. So you need one power of epsilon to produce the dark photon, and of course you need another power of epsilon to see the to detect the dark photon in the field sensor. So there must be an epsilon square in the prefactor in the when you do the calculation of the detection of the field strength. And as we mentioned previously, that all the physical effect must decouple when we take the dark photon mass to be 0. So there must be some kind of a positive power dependence of the dark photon mass in front of the prefactor. And it's important to figure out what exactly this n is corresponding to, is either 2 or 4. Okay, so before we get into the details on whether n is 2 or 4, let's just mention one kind of enhancement to the signal. Yes?
Sorry, I have a quick question.
Yes.
When you were looking at the mass basis, you said that the dark photons basically couple with epsilon E.
Yes.
Right, and epsilon's very small.
Yes.
But it seems like if you have a perfect conductor, you mean perfect, and it blocks out normal
very good.
photons, it would block out dark photons.
Absolutely, absolutely.
So how imperfect
yes.
is their perfect
Absolutely.
conductor?
So you can do the calculation for the skin depth.
Okay.
And the skin depth should also scale like 1 over epsilon. So like your epsilon is, if you take like a 10 to the minus 9, then the normal skin depth of the frequency, let's say 1 centimeter, then you need a kilo or more than a kilometer of the shielding to really block the dark photon. Okay, so one possible improvement of the experiment is making a good control on the source and the detector. So if you replace this point source field by a coherently oscillating plane wave, then and on the other side of the wall, you attach a resonator to the field sensor and just tune the resonator carefully so that the resonance frequency is matched to the source frequency. Then you can enhance the signal by the coherent oscillating, the coherent enhancement inside of this resonator. And so now, since I replaced the point source by the plane wave, so you got this plane wave as the red line, and the blue line are is the dark photon field. The plane wave being generated by the source. And here, because the photon and dark photon they are generated by the same source, so they must share the same frequency. However, the dark photon in the mass basis, it has a mass term, so the wavelength will be different. And when you are getting away from the source point, you will see the dephasing between the blue line and red line. And the red line will be blocked, and the blue line will totally feel free to pass through the wall and get into the resonator and ring up the resonant. Okay, so that basically means for this estimation, we will add in an additional enhancement factor, which is the quality factor of the experiment, and it will be very important for us for the real experimental setup, because that's actually one of the reasons why we are talking to the experimentist, because SLAC has really the world experts on the strong field cavity, and they can take this Q factor like 10 to the 10 or 10 to the 12. So that's a huge enhancement to the signal. Okay, now let's figure out what exactly the correct dark photon mass dependence should be in this story. So let's just assume the source, you replace the point source as a wall of the experimental charge, electric charge. And there are actually two ways to oscillate the charge wall. You can oscillate up and down, and then you will generate the transverse mode of either the photon and the dark photon, or you can oscillate the electric wall back and forth, and that will only generate the longitudinal mode. And that's how we do our calculation, just to get an equation on the correct power dependence. And let's first focus on the transverse mode. And for the transverse mode, let's work in the interaction basis, because that will be more easy for the calculation. So you oscillate the electrons up and down, and you will generate the plane wave of the interacting photon. And at the meanwhile, because you are working in the interaction basis, just to remind yourself, the only way that you generate the dark photon is through the mass mixing. So you don't generate a dark photon from the source plane, but when you are getting away from the source plane, the red line, the interacting photon will gradually oscillate to the dark photon, and you will generate the blue line over here. And then the wall will totally kill the interacting photon part, because it's a shield, and it will block all the force that is experienced by the shield. So the red line is vanished over here, and you get the non-interacting photon will pass through the wall. However, the non-interacting photon, because it's non-interacting, so it won't interact with the test charge particle on the other side of the wall. So you need another time for the oscillation to oscillate from the dark photon, the non-interacting photon, to interacting photon. And for each oscillation, you will get oscillation factor like sine function, and the argument in the sine function goes like m dark photon square L over 2 omega. And in the limit where dark photon mass is very small, this argument is very small, and you can do the Taylor expansion. And then the leading power of the dark photon mass dependence will give you as is set to be 4. Okay, and that's why the transverse mode will decouple as the 4th power of dark photon mass. And the key point for this transverse mode is the shield will set the boundary condition for the interacting photon is explicitly require the interacting photon equals to 0 at the point. So you need another oscillation to get the interacting component. Okay. And now let's focus on the longitudinal mode. In this case, you just oscillate the electrons back and forth. Let's work in the mass basis, because it's more easy for the longitudinal mode. Because for a massless photon, if you oscillate the electric wall back and forth, you won't generate anything for a massless photon. But for the massive photon, when you do this oscillation, the longitudinal mode will be generated only for the dark photon. And let's see what will happen to the shield. So let's zoom into the wall, and assuming it has a finite width, then the longitudinal mode of the dark photon will also oscillate back and forth along the propagation direction, and the electrons in the wall will is able to feel the longitudinal mode of the dark photon, and the electrons on the wall will also oscillate back and forth respectively. However, this oscillation will not be able to generate any normal photon, massless photon, by this kind of oscillation, because massless photon doesn't have a longitudinal mode. So this oscillation will not be able to generate any massless photon on the other side of the wall. And it will, of course, generate another very small component of dark photon, but that's further suppressed by epsilon. So you don't need to worry about that. So basically, at the wall, you won't be able to impose the boundary condition of the dark photon at the wall. So it will the longitudinal mode of the dark photon will totally just feel free to pass through. And the crucial point is the boundary condition is different for longitudinal mode and transverse mode. Of course, you can do the field redefinition in the language of interaction basis, and you will find the interacting photon is not going to be vanished at the wall. Okay, and that basically tell us the dark photon mass dependence should have the 2nd power instead of the 4th power because of the difference of the boundary condition. And of course, everything what I'm telling you is in a kind of a hand-wavy way, and we of course did a very careful calculation, and we after the careful calculation we showed that the dark photon mass dependence is exactly the same as what we expected and the same as what I told you.
So can you go back to the other one and just
This.
and say again why you have the double? Oh, I see.
Because you now you can oscillate the electrons.
There's sort of an inefficiency of. I guess. Yeah, I guess I didn't really understand why why you get these two separate suppressions in this case. Could you just maybe quickly repeat that?
Yeah, sure. So the key point is the boundary condition. Okay, just imagine how you really block. Let's firstly forget about the dark photon. Let's say that I shoot a normal photon into the wall, and why the wall can block the normal photon is because the electrons on the wall can oscillate up and down and generate a plane wave that is in the opposite phase as the incoming wave on the other side of the wall. So when you linearly add up those two, you will get precisely equals to 0 at the wall. Okay. The same thing happens to the interacting photon. So you just you will generate a interacting photon plane wave that is purely exactly in the opposite phase on the other side of the wall, and it will cancel this.
Yeah.
Okay. And for this longitudinal mode, you do not generate so right. So on the for the longitudinal mode, you do not generate a red field, a normal photon field. So.
I know, but I guess I just didn't understand if you go back to the other one, if you generate some of the I guess it's using this different basis here.
Yes, that's right. That's right. Let me see.
Because you're saying that the boundary condition here is, it's the fact that somehow this is inefficient at producing this mode, but that mode is also inefficient to be detected.
Yes.
And you're using that basis because that's the basis where the shield's effect is.
That's right. That's right. Precisely. And why I'm using this space in the mass basis in this story because I only produce the massive photon. I don't produce massless one.
Okay.
Okay.
So it's a production from the,
The production is kind of similar.
Similar.
Yeah. The
So-
only difference is what kind of a boundary condition you impose over here. Yeah, in this case, you have to regenerate the interacting photon.
It's kind of hard to compare these two arguments because you're using these two different bases.
Yeah, actually,
So somehow in this basis here, you might think that, well, why don't you have since you're using physical standard model electrons, why don't you have an m squared to create it and m squared to detect it? Right? What's the difference?
Yes. So the difference is let's do everything in the interaction basis. Okay. Now I'm telling you what happens in the mass basis, and then I can redefine my photon and dark photon.
Of course, I know that. But
Yeah.
but I want to. Okay, fine.
But you will find that the field, the interacting photon field, doesn't vanish on the wall. So I don't need another time of oscillation. Right. The key thing here is it's purely vanished on the wall, and I need another oscillation to generate the red line. But in this case, I have already had my red line passing the wall. Right. Okay.
So when we do the measurement, does that mean we will also have a sizable interacting photon in this?
Mm-hmm. Yeah. You're detecting the interacting photon, yes.
Oh, okay. So both the interacting photon
And the non-interacting photon, you won't be able to see the non-interacting photon because it's not interacting.
Oh, I see. So the thing you see is
It's the interacting one.
yeah, of course.
Okay, so that's the picture, the general picture of the light to wall experiment. And now let me get into the detailed experimental setup. So there are basically two classes of the light to wall experiment. One is this laser-driven optical cavity, and one typical example for this kind of experiment is the so-called ALPS. And so in this case, you have the optical cavity, which are those gray bars, and you have the laser on the other side of the cavity. So the laser beam will oscillate, bounce back and forth in the optical cavity. And the black bar here is the wall. It will, if there is no dark photon, then the laser beam will never be able to pass the wall. And on the other side of the wall, you have another set of optical cavity tuned to be the same as the previous in the emitter side. And if dark photon is produced, then you will be able to see some kind of a signal on the other side of the wall. Okay. And the other class of the electrical experiment is this resonance microwave cavity experiment. It's just a similar story, but replacing the laser beam and the optical cavity by microwave cavity, and there's a high frequency wave generator. Okay, so those two classes of experiments have their own pros and cons. So the good point for the laser-driven optical cavity experiment is, first of all, it's driven in a much higher frequency than the microwave cavity. So because the frequency of the photon in the laser beam is like EV, and the microwave cavity is like 10 to the minus 6 EV. So in principle, the laser-driven cavity experiment can probe a much larger dark photon mass regime than the microwave cavity. And the other good point for ALPS is the cavity length, which is the separation between those two mirrors, is much larger than the wavelength of the photon running in the cavity. Okay, so that will help us to enhance the signal. On the other hand, the bad points for this for the ALPS setup is the quality factor is limited. It's just a technical issue. The optical cavity is not going to be enhanced or improved in short real time. So it's like 10 to the 6 is limited. And the physics reason why we don't like the laser-driven cavity experiment is because only the transverse mode of the dark photon is efficiently produced. The longitudinal mode of the dark photon is not going to be efficiently produced, because that's the longitudinal mode of the dark photon is produced by the electrons oscillate on the endpoints of this optical cavity. So the longitudinal mode will go up and down, and transverse mode goes left and right. And if you just place the receiver cavity on this side of the wall, then you won't be able to see the longitudinal mode over here at all. Of course, you can say that I can move my receiver cavity into the up-down configuration. In that case, you do receive the signal from the longitudinal mode. However, you will at the meanwhile lose the benefit having a very long cavity arm. So we also did the calculation for ALPS, and it turns out the reach capability is much worse. So it's not going to be the focus of this talk at all. And on the other side,
probably I
yes,
missed it. Is there
yes,
some particular reason for caring about the longitudinal mode?
Oh yes, that's the key point of this talk, which is for the light-to-wall experiment, the longitudinal mode will generate a much stronger signal compared to the transverse mode when the dark photon mass is very small. And for the microwave cavity experiments, first of all, the technical issue is the very high quality factor can be achieved. It can be as high as 10 to the 10 or even 10 to the 12. And the physics reason why microwave cavity is interesting is because the longitudinal mode and transverse mode, they are equally produced. And so that's actually the reason why we are focused on this microwave cavity experiment in this paper. And of course, the bad point is the operation frequency of the microwave cavity is much lower than the laser frequency. So in principle, you can only probe a much smaller dark photon mass region, and also the cavity length is comparable to the wavelength of the photon oscillating in the cavity. So it doesn't have the privilege of the long arm compared to the ALPS.
So could you say again, what do we do to enhance the quality factor? What are the things?
It's basically just the dissipation of the photon or the electromagnetic field inside of the cavity. So for the laser, the optical cavity is just the photon will get lost in the environment after it's oscillated for a million times. But for this microwave cavity, I don't know why exactly the quality factor is better, but the energy dissipation is much better. is much smaller.
The quality, sorry, the quality factor is the narrowness of the resonance
Yes,
that
that's
you
right.
can read out. So
Yes.
it's an experimental thing that says, how theoretically you want to couple this thing to an oscillator that resonates at the same frequency.
Mhm.
And you would like the dissipation of that oscillator to be as little as possible,
Yes.
so you get a super narrow peak.
Exactly.
And so it's just experimentally, how well can you do that?
Mhm.
How well can you couple this to an oscillator with a non-damped oscillator at the same
Yes.
frequency?
So the idea of this emitter cavity is that the photon and the dark photon just sort of sit for a while, bouncing back and forth.
The photon will bounce back and forth.
Forth.
While it's bouncing, it has a small probability to convert to dark.
Slowly convert to dark
Yes, that's right.
photons, and so the longer it sits in the cavity,
No, dark photon doesn't sit in the cavity. Well, once it's produced, it will get lost. But
okay.
there is also a very small
But the
probability.
larger the photon sits in the cavity, the better, or not? Does it matter?
Sorry, say that again, please.
Does it matter if the photon is sufficiently bouncing
yes.
back and forth in the
Yes,
cavity?
the more times the photon you can bounce back and forth, the better the experiment will be.
But
That's controlled by the quality factor.
But never reaches the level of the laser.
No, actually, for the
enhancement.
microwave cavity, the quality factor is much better. So that means the photon can bounce back and forth much more with more times
That's
compared to the
fantastic,
laser.
yeah, okay.
Okay, good. Okay, so now let's focus on the microwave cavity experiment. So there has already been several existing experiments using the microwave cavity to carry out this light wall experiment. One is carried in Australia, and I don't know what happened to them, and the most recent result is from 2010. And the ADMX is aiming to look for the axion dark matter background, but they are also run they also run their own light wall experiment at the beginning stage. And the third one will be the focus of today. This so-called cross is ongoing and is somewhere carried out in CERN. The reason why we want to focus on cross is very interesting because they are doing this light wall experiment for both axion and dark photon. And this is roughly the picture of their cavity. And they actually have two different modes for the cavity. One is called this EM mode, the other called TM mode and TE mode. Okay, so let's say that I put my cavity on the left-right configuration, and if I oscillate the electric field back and forth in this way using the TM mode, then I can, on the other side of the wall, I can detect the longitudinal mode of the dark photon. And if I oscillate the electric field in a kind of a circular way, in this TE mode, then I only produce the transverse mode of the dark photon. And it's actually interesting for cross because in their axion search, they used this TM mode. However, when they do their search for the dark photon, they use the TE mode. So they are precisely using the wrong mode for the dark photon search. They on purposely switch to the wrong mode. And of course, the difference between the axion search and dark photon search is whether you have a strong background magnetic field or not. And of course, you can use the null result of the axion search and reinterpret everything as your dark photon search. And that's why cross is very interesting. And so here is the constraint plot that I showed you before, the gray things. And the dark blue region is the cross published result for the dark photon search from their light wall experiment. And however, if you just use the axion search result, which is also available in their experiment, then you can reinterpret their axion search result as a new dark photon search result, and that's actually the parameter regime that they really probe in this experiment. And you will see that there is a very small difference on the T point. That's because for different modes, they will have different operation frequency, and they have a little bit different quality factor. And that's why there is a very small difference. But the crucial thing here is when you operate the experiment in the correct way, then you can really achieve a much better experimental search region than the transverse mode if you use in the dark photon search. Okay, and so that's actually their beginning stage of the experiment. That's their proof of concept running. And if someday they can improve their experiment, for example, running for a longer time, then if they can reach like epsilon 10 to the minus 11 at the T point, if they keep running their experiment in the round mode, then that's the parameter regime that they are going to probe. However, if you operate using the correct mode or placing the cavity in a correct relative position, then that's really the parameter regime that you can probe in this experiment. Okay, so it's kind of interesting and it's good for us because SLAB has really the very good experts on the strong field cavity. So we are talking to the experimentalists as well in SLAB, and hopefully we have already submitted our proposal, and hopefully we can get some money and carry out the experiment locally. And those are the two sets of benchmark numbers the experimentists set to us. So it's not some random number that's not realistic at all. So assume you have two stages of operation. One stage is assuming the field strength in the emitter cavity is like 1 Tesla. And the size of the cavity in the first run you set it to be 10 centimeter. The quality vector is 10 to the 10, and you just run it in normal temperature, like 4 Kelvin, and you run it for a month. 4 Kelvin is very easy to be reached by put it into the liquid helium, and that's the parameter regime that we can reach in this experiment. Yes.
I think I realized something very basic I don't understand. What is the role of the magnetic field for what you're doing?
Oh, you mean this one?
Yeah, because I understand what it is for axions, but what is it?
Oh, sorry. This is not the background static magnetic field. This is just you can say my electric field. It's also 1 Tesla.
Oh,
yeah. This is just
measuring the strength of the oscillation. It's the
precisely.
amplitude.
Yeah, it's the field you dump into the yeah. I'm sorry. Yeah, this should be more clear.
Very confusing.
Yes. So for the axion beyond this field, you also put in another background static magnetic field.
Okay.
That's the difference. And for the second stage, if you can further cool down your experiment to be 0.1 Kelvin, which is definitely doable in the dilation fridge, and that has already been carried out in ADMX search. So it's a reasonable temperature to assume. And the quality factor can be improved to be 10 to the 12. And we changed the size of the cavity from 10 centimeter to 1 centimeter just to show the different positions of the T point. And we run the experiment for a year, and that's the experimental result, the experimental expected limit probing regime.
But what roughly happens to the stage 2 if you stay at 10 centimeters?
Oh, it will stay here, and let me see. I can't figure out whether the T point will.
It's not better, right?
No, it will definitely be better because it's running in a longer time, a lower
No,
temperature.
but I'm saying if you keep everything else the same and you just make it smaller,
Oh,
it can't be getting better, it must be getting worse, otherwise you make it smaller. It's easier. So,
I'm not sure. There are several length dependence because it depends on
It
the.
probably doesn't just control the heat, it probably changes a lot of other things too.
That's right. And how the peak will shift, I'm not sure. Okay, so that's everything about the light wall experiment. So now let me get into the third part, the very last part of the talk, which is making an additional assumption that dark photon is the dominant component of the dark matter. Okay, so first of all, a boson with very, very small mass can be a good candidate of dark matter, cold dark matter. One typical example is the axion field. It can be very cold, and because the mass is very small, if you take the local dark matter energy density 23 GeV per cubic centimeters, you will get extremely high occupation number for those very light fields. So it's more proper to treat the dark matter in this very light dark matter scenario as a background coherently oscillating background field instead of each individual particles. And axion can do the job, and the dark photon can also do the job. And the correct way to think about the dark photon dark matter is yeah. Oh. it's a coherently oscillating dark electric field. And just to get a rough feeling on the size of the dark electric field, you can convert the local dark matter energy density, and you get the dark electric field like 2000 volts per meter, which is an extremely large dark electric field. The problem is it needs some power of epsilon to suppress the interaction. So it's interacting so weakly, and it's not easy to see. And the dark is a dark electric field, so it has a preferred direction. It will randomly direct in different patches of the universe. And of course, it's a Lorentz symmetry breaking background. However, it's really just hard to see because it's coupled so weakly. And the dark electric field is oscillating with a fixed frequency, and the oscillating frequency is set by the dark photon mass. And because we know the virial velocity of the dark photon, of the dark matter in our galaxy is like 10 to the minus 3. So the coherent time of this dark photon dark matter is 1,000,000 times of the period, oscillating period of the dark photon. Okay, and there is some kind of a cosmological interesting cosmological concern about the dark photon. First of all, if you trust the result from Bessa, then you say my inflation, the Hubble during inflation is very high. It goes like 14th GeV. That will cause some problem for the axion field because that may introduce very large isocurvature perturbation if you have an axion field during the inflation. However, there is a very crucial difference between axion field and the dark photon field, and the crucial difference is the long wave modes of the dark photon field will decrease as 1 over a squared. The energy density deposit in those modes will decrease as 1 over a squared. In the scalar case, the energy density will fix as a constant. So that's a very different scenario or result in the dark photon compared to the axion. So that will automatically solve the problem for the isocurvature perturbation.
And just for the transverse modes, not
no, that's for the longitudinal mode. So the transverse mode will decrease even faster. So it's actually kind of easy to understand why the energy density will decrease as 1 over a squared, because you know the normal story for the scalar field is once the mode is outside the horizon, the field value is fixed, and the energy density is just mass squared phi squared. So the energy density for those modes is also fixed. However, for the vector field, when you say my field value is fixed, you have to tell me whether you are focused on the a upper mu or a lower mu, and you can write down the equation of motion for both indices, and you will find that a lower mu is actually the one that will be fixed when the mode is outside horizon. Then when you write down the energy density of the vector field, it goes like mass squared, a upper mu, a lower mu. So you need another factor from the metric, which is 1 over a squared, to lower down the index. So when you fix the a lower mu, when the mode is outside horizon, the energy density corresponding to that mode will be decreasing when the universe is expanding, and that's the crucial difference. Okay. And if you trust if you take the Bessa hint, treating the inflation scale to be the Hubble of the inflation to be 10 to the 14 GeV, and to get the correct dark matter abundance in the dark photon, you will get the dark photon mass like 10 to the minus 7 eV, which is kind of a numerical coincidence that this 10 to the minus 7 eV will just fall right into the best probing regime in our experimental proposal, which I'm going to show you later.
What determines the starting density?
Sorry?
Something has to have made this abundance of dark photons.
Oh yes, you just produce those field during the from the fluctuation during the inflation.
But what is the mechanism for that?
It's just the quantum fluctuation when the universe energy density of the universe is controlled during the inflation.
So that's independent of the mixing epsilon?
No, yeah, that's independent to that.
Okay.
It's the similar story as what happens to axion. You can also use the inflation to generate the axion through the quantum fluctuation of the axion field during the inflation. But that may cause the problem for isocurvature perturbation. if your inflation scale is too high. Okay, so now let me show you that after, so all the covered region is the experimental constraint to the existence of that dark photon. Now, since we put in an additional assumption that the dark photon is also the dominant part of dark matter, then you have to consider whether that will cause any additional constraint. And it turns out the CMD constraint will be really the dominant one in the low mass regime. And in this case, as I told you previously, the CMD constraint is oscillating the CMD photon to dark photon. But in this case, it's really oscillating from the dark photon into CMD photon. You will dump more dark photon into real photon, and you will see the distortion of the CMD photon of the CMD spectrum this way. And that's a much stronger constraint than before. And still, those two lines are the lines that just to show that if you really operate the light wall experiment properly, then you can even probing the regime of the dark photon dark matter regime. Okay, so ADMX is an experiment searching for the axion the cosmic axion background, and it is automatically sensitive to the dark photon dark matter background. However, the ADMX is restricted by the probing regime of the ADMX is restricted by the cavity size. So it only probe the dark photon mass regime like 10⁻⁴ or 10⁻⁶ eV. And of course, there is another kind of a candidate for a very good oscillator or resonator, which is the LC circuit. It's basically just the radio. And you know that you don't need to squeeze your radio to change the channel, you just turn the knob. So if you replace the cavity used in the ADMX experiment, you can very easily probe a much wider and lower frequency regime than what can be probed by using the resonant frequency. And so that's a very simple way to probing a much better, wider dark photon mass regime. And there is some kind of a subtlety about detecting the dark photon dark matter background. So previously I told you the dark photon dark matter background should be treated as an oscillating dark electric field. And of course, you must operate your experiment in a shielded regime because you don't want to listen to the normal stand model of photon. You just want to listen to the dark photon. So you have to put your LC circuit into this shielded region. And there is a very non-trivial and very subtle back reaction from the shielded regime respect to the dark photon field, dark electric field. So it actually can be understood very easily by taking the limit where dark photon field is oscillating very slowly. Then you can treat it approximately as a constant dark electric field. Then you zoom into the wall of the shield. The free electron on the shield will feel the force generated by the dark electric field. So they will run. There will be a charge displacement generated by the free electron on the shield, and for example, more positive over here and more negative over here. So the charge displacement will generate opposite real electric field. And if you put a test charge particle in the inside of the shield, you'll see the force acting on the test charge particle is the sum of the oscillating of the dark electric field and the real electric field caused by the small charge distribution, small charge displacement on the shield. So that basically means I am not going to be able to directly detect the dark electric field. However, we know the dark electric field is also oscillating as the frequency of the dark photon mass. So there is a kind of a very small electric current being generated on the wall of the shielding of this shield. So this very small electric charge current will generate a real magnetic field, and that should be the leading order effect, and that's the correct field that one should focus to probe. And there are also some kind of other experimental proposal similar to this one, but they totally missed the back direction of the shielding effect, and they are proposing to look for the dark photon, like the wavelength comparable to the size of the galaxy. And if that's sorry, I forgot to mention this kind of a shielding effect will introduce a suppression factor, goes like m dark photon times r, where r is the typical size of your shield. So if you forget about this suppression factor, or if you miss this suppression factor, and when you are looking for the really light dark photon mass region, then your estimation of the signal size is totally off, and it's very important to realize this subtlety about the suppression factor. And you can put in the after you read this, you can put in the LC circuit and aiming to look for the real magnetic field generated by the shield. Okay, so we are also talking to the working with the experimentalist very closely, and that's the two benchmark points that they gave us for stage 1 and stage 2. And the one is using a smaller shielding size and operating in a higher temperature, and it's doing 1 year scan. And the second step is using a larger shielding size and further cool down the experiment so that you can reduce the thermal noise. And those are the probing regime in our proposal. And it turns out to be just a numerical coincidence that if you take the superficial value from BASF and assuming the inflation scale, the inflation Hubble is 10 to minus 14 GeV, then the preferred value of dark photon mass is like 10 to minus 7 eV, which is right in our best probing regime. Okay, so now let me conclude.
See, one thing
Yes.
what's causing the very sharp
Oh, we just
cut off?
stopped here. We just stopped here. We actually have, I mean, because up to this step, you have to consider whether it's better to use LC circuit or using a cavity.
Right.
If you are using a cavity, then it has nothing to do. It's not different compared to ADMX.
I see.
Yeah. So we basically just
The
cut
LC
off
circuit only works up to
in the lower frequency. Yeah. Because it will be much better to use a cavity instead of an LC circuit. Okay. So let me summarize. So first of all, I'm talking about the detection of the dark photon by the light wall experiment, and this is only making the assumption that dark photon exists. And the most important thing is that there are both transverse mode and the longitudinal modes of the dark photon in the mass spaces, of course. And in such kind of experiment, the signal strength of the transverse mode goes like dark photon to the fourth, dark photon mass to the fourth, and longitudinal mode of the signal size goes like dark photon mass squared. And this is because of the boundary condition. And if you take whatever existed in the current experiment, you just need to properly position your cavity or using the correct mode when you are operating your experiment. Then you can parametrically enhance the probing capability when you realize the importance of the longitudinal mode. And then the last part of the talk is making an additional assumption that dark photon is dark matter. First of all, is the very light dark photon can be a very interesting dark matter candidate, and you can detect it by a shielded LC circuit. And the sensitivity of the experimental proposal just numerically coincidentally land in the correct, the cosmologically interesting mass regime. And for both parts of the talk, we are talking or working with experimentalists very closely, and hopefully both of the part can be carried out locally in Stanford or SLAC. Yeah, that's it. Thank you.
A later question, I'm still trying to understand more about
Yes.
the cosmological picture.
Yes.
So the photon prime is produced by quantum oscillations, quantum fluctuations,
Yes.
or whatever, and its density, does it annihilate it all, or
No, it's not going to.
it just sits there?
Yeah,
after-
once you produce, you will just stay there.
once it-
The only thing that it will feel is just the gravitational effect.
Right, okay, so it doesn't keep oscillating enough to regular photons that any of them
Yeah, once the
disappear.
mode is outside the horizon, the field value will be fixed.
Yeah, I see, that's determined by the mass.
Yes, that's right. So when the mode is coming in, when the Hubble match to the mass, then the star will also.
Yeah, yeah. So that's where this 10 to the minus 7 comes
Yes,
from.
that's right. That's right.
If it's any larger than that, then you would get some reoxidation or something. Okay.
So actually, I have a related question. So does it mean for that story, the size of epsilon is not important? The mixing, the size of the mixing. I mean, for the dark matter story.
You mean just from the production point
That's
of view?
right.
That's right. That's right. It doesn't matter for the
So in
epsilon because
principle,
it's just gravitationally producing.
Right.
Yeah.
So I wouldn't expect like for some large
Yes,
size
in
of
principle it can be over here.
yeah, all the way down.
Yes, that's right. So, but the detection really care about the epsilon.
That's
so,
right. Okay.
Yeah.
So any other question?
Yeah, maybe,
Yes.
maybe it's a bit related.
Uh-huh.
So in all your analysis, don't care about how the mass for the dark photon is.
It cares about the mass of the dark photon because
So
of
what
this.
okay, that's the mechanism that breaks the X-ray one is not important.
Very good. So, so as I told you that there are basically two ways to generate the mass sum of the dark photon. One is from the dark Higgs. However, if you just give me the most natural Parametric regime of the dark Higgs, then you should also expect there is a very light dark Higgs particle instead of the dark photon. However, in that case, if you really make additional assumption that there is a dark Higgs, then the real experiment should be really focused on the dark Higgs because the dark Higgs, you cannot redefine the dark Higgs away. So all the physical effect will be almost flat if you make the assumption that the dark Higgs is there. Then you shouldn't focus on the dark photon at all. But because this is just a U1 gauge group, so it's just a UV complete if you add in the Stackelberg mass term by hand. So
can I understand that? What do you mean? What is your point about the dark Higgs?
the dark Higgs is once it exists and once it's very light, then you should really design your experiment to look for the dark Higgs.
Like in the wall experiment, you're basically
Yeah, you
saying
can produce the dark Higgs.
There's no boundary condition for it at the wall.
There won't be boundary condition.
Yeah, that's what I'm saying.
Yeah.
So,
See, why is that?
well, it's just because it's pure. It has no mixture with any standard model field.
I see.
Yes. Even your electrons also, well, it doesn't generate
So
Absolutely.
what's happening in the early universe in such a case?
if you have a dark Higgs,
Like dark Higgs.
then the story will be more or less like the axion case. Then you will produce both the fluctuation for the dark Higgs and the dark photon.
Mm-hmm.
And the dark Higgs will remain, the field value of the dark Higgs will remain fixed. And then the energy density associated to the larger scale mode of the dark Higgs will remain exactly the same as a constant. For the dark photon, it's really the longer mode will decrease. So in that case, I should expect the dominant part is the dark Higgs. Yeah.
Okay. So no more question now. But thanks, Zhao, again.